Fischer Tropsch Slurry technologies. As Professor David has told me, there's a lot of research coming along on the Fischer Tropsch Slurry systems, which are also familiar with them, and I'm getting familiar more as I talk with different people involved in the center. Most of this work has been done in Sasol, South Africa. That's why before I start, I should acknowledge the contribution of Sasol Technology, which is a part of the Sasol group. Sasol Technology, which is a part of the group that supplies all the technology and the engineering support for all the operation of the Sasol group. Especially the process development department, where I worked after '93, after the commissioning of the commercial slurry bed process. And the slurry bed team, which surprisingly were not more than 7 people. The project managers, the engineer for the cooling train, the refinery engineer, and the plant engineer, and Dr. Espinosa, who is the catalysis guy. The outline of my presentation, I don't want to bother you with so much of the background of Fischer Tropsch processes, because I know that you're familiar with it. And I'm going to give you some background on the slurry bed process in terms of the commercial and the large plant, pilot plant experience that we got. Some commercial experience in terms of Fischer Tropsch attempts to commercialization. The Sasol 1 SSBP, and this stands for Sasol Slurry Bed Process Development and Operation, that we have already from, basically we have 2 years already in operation. We commissioned the commercial plant on the 1st of May, '93. Some catalyst considerations for future development, and the conclusion and recommendations that we see from Sasol's point of view after considering all these points. One thing it has been mentioned that Fischer Tropsch is isothermal, and that is true for a big bubble column. The dimensions that I mentioned here are like 3-foot diameter and 20 meters long. That's a pilot plant. And a commercial plant is 5-meter diameter and 20 meters long. That's the dimension that we're looking at, and the isothermal behavior can be seen. And interesting enough is that if you're expecting hot spots, you're not going to find it. What you're going to find is cold spots, if any. And that's very close to the cooling coils. That's our experience in terms of isothermal behavior. Due to fluidization, the particle sizes that have been used, are below 200 microns. So therefore, the effectiveness factor has to be close to 1. Low pressure drops is one characteristic of the slurry bed process if we compare with fixed bed process, similar to the Schellman laser plant. They're using fixed bed. I'm going to discuss a little bit later that, but the low pressure drop is characteristic for the slurry bed process. In Sasol's experience, the pressure drop across the fixed bed is around 3 bars. So it's only the static head of the liquid which represents the pressure drop across the slurry bed. And in terms of low capital cost, compared with a fixed bed of similar capacity, we're talking a 50% reduction of capital cost. Since many people here are more catalyst oriented, I'll give you a little bit of the difficulties and complexities of the slurry bed in terms of process. As you know, the reactants has to be in the gas phase, and has to be fused from the gas phase to the liquid through the gas-liquid interface, and then diffused from this liquid interface to the bulk of the liquid through the liquid-solid interface to reach the solid, and then diffuse through the pores, reach the active site, and travel all the way back. Those are kinetic resistances. And many people, many researchers has been stating that mass transfer is a controlling step in the Fischer Tropsch process. I'm not going to talk at this time with mass transfer and the limitation of mass transfer in slurry bed process, but one has to be aware that there is always a presence of mass transfer resistances. to complicate a little bit the picture on the slurry bed, we have to understand that one of the characteristics of the slurry bed is that it has flexibility to remove catalysts or to add catalysts. And if we're looking at fixed bed, we need to come offline, open the reactor, drain the whole catalyst, and put back new catalyst again. However, in the slurry bed, this can be done online. However, if a sulfur poisoning happens and sulfur gets into the system and poison the catalyst, the whole inventory of wax and catalyst can be removed from the slurry bed, come offline, put back again another batch of wax, another batch of catalyst, and come back online. This whole operation can be done in less than 8 hours commercial experience. One point that I have to mention though is that if we look closer to the reactor, what we're going to find is that internals inside the reactor has to be considered in anything that we do. I talked with several people that are looking at modeling of the Fischer Tropsch Slurry bed process, and they forget that in all the Fischer Tropsch synthesis reactor, they have to be a cooling system. Fischer Tropsch is exothermal, and also water gas shift is exothermal. So therefore has to be cooling coils. And cooling coils has to have some beams for supports, and has to have pipe for catalyst inlet and catalyst removal. Those complicate a little bit the picture. And the slurry bed has to have bank of coils and piping coming in and piping coming out. Not even to mention manholes and ladders in order to work on that for maintenance. So there are a lot of internals inside the reactor that has to be considered when you're looking at scale up. I'm just giving you the background how this process has been developed. And if you look at each section, just for modeling, you should be looking at stirrer reactors in each section. And you can go along, you go at very tall reactors, you have to have several of these, one above the other. Just to mention this is that you cannot have one single cooling coil system because there are mechanical considerations. Vibrations will limit your length of the cooling coil to 7 meters, no more than that. You will be facing problems with the stability of the system and mechanical stresses. Even if to complicate the pictures, I'm talking to some people here, is that the decision to go to a bigger reactor or two in series is a difficult one. Not only for capital costs, but also to how to apply the reactor that you just define or you just develop into the most economical environment. This is the recycle scheme, and this is one-third operation, however, with two reactors in series. As you can see, there are two condensers and two separators. However, there is only one condenser and one separator. However, these are smaller systems, these are bigger systems, but there is only one control loop. One control loop, and there are two control loops. So there are different systems that has to be considered in terms of economics, and what are you looking at for your reactor. I'm going to pass now to discuss the commercial experiences that we have in Fischer Tropsch. One is the Moss gas synfuel gas. The Moss gas is a plant that has been started in December 92, January 93. It is based on the use of offshore natural gas, and this is the capacity, 2,400 tons a day of gas oil. The technology that is using Moss gas is similar to the one in Sasol. In the circulating fluidized bed that you can see here, this was initially the Kellogg technology, where the gas comes this way. This is the catalyst being stored here, and there is a standpipe, a slide valve. It comes through the riser. The reaction mostly happens here, and there are heat exchangers all around here. So the gas and the solid comes through the gooseneck, through a cyclone. The gas is separated this way, and the catalyst separates that way. So the catalyst is in a continuous circulation. This technology was used for MOS gas. And they have 3 reactors, circulating fluidized bed reactors working with iron catalyst. This iron catalyst is fused catalyst. The total cost of the whole plant was $5.1 billion. However, the synthesis plant is only 600 millions. However, this was a political thing because Fischer Tropsch is not economical at this moment, so why to put it? It was a political thing where the break-even point was $35 a barrel for the, if we compare with the supply of oil. However, this was done when the conflict of when the Iraq attacked Kuwait. So the scenario, the political scenario was different. If we look at alternative technologies for fluidized, gas-solid fluidized systems, Sasol has developed what is called, initially was called a fixed bed fluidized system. That if you can see that these are 2 different reactors, similar capacity, however, only 50% of the cost in terms of capital cost. It's a similar system. It's an empty reactor, have cyclones on top and cooling coil, and it's just a gas distributor that just keeps the whole system fluidized. Coming to the US and looking for slurry bed experience, we find a fuel core synthesis, what we call high-tech plant, now the Rentec plant. It was the first attempt to use non-fuels, methane that has been produced in non-fuel, and the capacity was these barrels per day on the diesel, 50 naphtha, and 80 wax. The idea was to produce high-quality wax and high-quality diesel, which can be sold by Pueblo, Colorado. And they were using one single slurry bed reactor with iron catalyst. The cost was $60 million. However, the problem was with them is that one, the methane concentration in the landfill gas was very low, and the other one was that the catalyst wax separation didn't work out. The iron catalyst presented a very high attrition rates, and therefore they couldn't be separated from the wax. The other commercial experience, which I'm going to talk, which are the Shell, the Sasol, and the possible Exxon, are going to have this scheme. And this is going to be done for diesel production plant. Actually, at this moment, nobody is looking at wax production. The wax market has been already taken by Sasol with the Argy reactors, and there is no much margin to put more wax into the market. So therefore, all the Fischer Tropsch heavy hydrocarbon will be directed towards hydrocracking and diesel production. So this will be the typical scheme for a diesel production plant. And whether it comes from coal gasifiers or natural gas reforming is really depending on the H2CO ratio that is going to be fit to the synthesis plant. If we're looking at coal gasification, we're looking at a new generation of coal gasifiers with low H2CO ratio. We can mention Shell and Sasol, these gasifiers, on natural gas reforming with a mixture of partial oxidation and steam reforming, just to have an equilibrium in terms of heating duties. This synthesis gas has to pass through a purification zone. This is very important if you're looking at cobalt, because the cobalt is so expensive, 30 times more than iron. So therefore, any sulfur has to be removed. Shell Malaysia is using the ICI technology, which is based on zinc oxide in a fixed bed. Sasol, in Sasol South Africa, is using cold methanol wash. I don't remember the name of the process now, but it's a cold methanol wash to remove all the COS and the H2S. And then has to go to a slurry bed, which the wax has to be separated, and then hydrocrack for production of diesel, and the light production will go to a separation, oligomerization to increase the naphtha production and the diesel. This is, I'll refer that later. This is the Exxon AGC21. I don't know to whom I mentioned this process. This is the excellent alternative for the production of synthetic diesel. This is we're looking at fluidized gasifiers. This is that for the natural gas, which has to have sulfur trap and then try to be reformed. All the heating and recovery of heat, and this is the slurry system. This is the carbon system, and they don't mention about how they separate. However, the patent mention about the use of filters inside the reactor. The catalyst that they're using is cobalt, and supported with different types. Some of them say titanium, some say alumina. However, the moment they support it, then we're looking at very strong catalyst, and this catalyst does not break, so therefore can be separated very easily. And since this is a spray dry, it's very easy to filter, and actually does not show any problem in terms of agglomeration. The Shell middle distillate synthesis plant is in Shell in Bintulu, Malaysia. It's based on natural gas. The capacity of the plant uses 100 million of cubic feet of natural gas a day and 10,000 barrels per day of production of synthetic fuels. They have 4 fixed bed reactors, and the cost was $660 million. The reactor technology that they use is a very old one. The catalyst is new and very good one. However, the reactor itself, this is a Lurgy type of fixed bed, and the Shell Malaysia is very similar to that. We have some pictures of that, however, I don't have it in here. The gas comes in, and it's a trickle bed basically, because you're producing wax from the top, and it just trickles down, and the water is being pumped, try to cool down the system. For cobalt, you have to reduce the fixed bed tubes from 1 inch to 1.5 inch for heat removal. We know that they faced a heat removal problem when they tried to start the plant, and they had a fire in the synthesis plant. And they came online only in December 93, I'm sorry. Talking with the Shell guys about their catalyst performance, it has been claimed that their catalyst can last 5 years. However, they only are 1.5 years online. So what he actually told me is that we have to wait 3 years and a half more just to justify the claim. Why is this? Is because the cobalt catalyst is very sensitive to sulfur. It can be regenerated if it's only oxidized. However, if it's sulfur, then the loss of the catalyst is permanent, and the cost is very high. Coming back to Sasol experience, the Sasol slurry bed process is based on the existing Lurgy coal gasifiers. I've been talking the whole morning. The H2CO ratio of the coal Lurgy gasifiers can change between 2.2 and 2.0. One can work on those limits. One can bring it down a little bit to 1.8, however, cannot push it that hard. Lurgy coal gasifiers are fixed bed gasifier, where the pellets are put from the top and the oxygen and water is pumped from the bottom. And the capacity of this slurry bed, which is only one reactor, is 300 barrels per day. The dimension of this reactor is 5-meter diameter and 22 meters long. And the break-even point was $23 a barrel for a new plant. However, we should mention that we use existing equipment, and the whole thing was built in an existing scenario. One limitation of this development was that this was placed in Sasol 1 environment. Sasol 1 is already a plant that was built in the 1950s. So, and the market for this slurry bed process has already been defined. So before we start the project, we knew what product distribution we need to produce. It's not just produce and whatever we will sell it. We already have a product distribution, so we cannot push that conversion harder. We need to just make whatever they need. and the distribution has to match exactly the marketing requirements. So this was done in SASO 1, and the reactor was placed in this part. This is a 76 picture, and the reactor I'm going to show you later is going to be placed in here, and these three reactors, which are the CFBs, the circulating fluid gas reactor, has been shut down, and the whole gas that came here was taken by one single reactor. This is the slurry bed process. We use the same fixed fluidized reactor. We just took the cyclones out and put wax in it and run it. We change, of course, the gas distributor, and we have the slurry bed process. It's just an empty vessel with cooling coils. That is how cheap it is. That's why the capital cost is very low. And the dimension of that was 5 meter diameter and 22 meters long. That's the dimension of the commercial plant. If we look at the SASO 1 scenario, okay, the synthesis gas was used to go to the argy reactors of the Synthol. Synthol is for diesel, for gasoline production, and the argy was for heavy hydrocarbons. The temperatures in the argy was around 220 degrees C, and the Synthol was about 350. So the product distribution is completely different. The new idea with SASO 1 was to shut this whole train and use this gas to produce more argy products. And therefore, we needed to match exactly the argy distribution. And the challenge was to put a slurry bed process, take the whole gas that came to Synthol and match exactly the argy products with a new reactor, which is the slurry bed process. So the whole thing just came back again. There is almost nothing on gasoline, and everything goes to diesel and waxes. Before I discuss the catalyst selection, I'd like to discuss with you two things. I mean, there is a lot of discussion between iron and cobalt catalysts, which is better. There are many considerations that I'm going to talk later on about these two catalysts. At SASO, we are much more familiar with iron catalysts. We have been working with them for 40 years already. So we know how to work with iron catalysts. Cobalt is a new thing, although there's a lot of promise in it. It hasn't reached levels that we can trust it, at least for commercial applications. The water gas shift and the Fischer Tropsch reaction are shown here. And the important part of this is that we should bear in mind that water gas shift produces hydrogen that is needed for reaction in the catalyst pore. It doesn't produce it in the gas phase, in the catalyst pore, so it's ready for reaction. However, this CO that is needed for reaction has to travel all the way from the gas phase through the liquid bulk to the catalyst. Okay, there is a slight difference in how these reactants reach to the particle sizes in terms of mass transfer rates. We can discuss further if you're interested in this point. In terms of iron catalyst, the kinetic expression is this. This is the result of Dr. Espinosa working at SASO and presented in Anaheim, California. He has a theory that unifies all the catalyst experience, iron, and produces this unified version. The changing one can explain all the changes and expression that many researchers have found in terms of iron. In terms of cobalt, this is the expression that we found that fits most of the experience in terms of cobalt. And the water gas shift, this is a typical expression that everyone uses. Nothing fancy on that. We look at the iron catalyst to see whether it's a good or bad catalyst, does it need to change or not. We have to realize that it gives high alpha values at reasonable temperatures. I have to point out what I call reasonable temperatures. Some some researcher has forgotten that in commercial applications, the heat that is being generated in Fischer Tropsch reactor has to be removed with some liquid, whether it's heating oil or it's steam production. What I suggest is that boil feed water, so we produce steam that can be used later on by a refinery. If the temperature of the reactor is high enough, we can discharge steam into a high pressure header and therefore produce electricity. So this will increase the economics of the process. However, if we operate at very low temperature, we're going to produce very low pressure steam, and that's actually the case of cobalt. Of cobalt, if you are working on an operation of 220 degrees C, you're only going to discharge to a header of 18 bar, which is readily available already in refineries and actually is not of much value. The iron suffers the activation in terms of sintering, poisoning, and fouling. Iron produces a lot of water due to Fischer Tropsch and also water gas shift. That's changed the water into CO and hydrogen. I was explaining to some people in the room that if we're looking at catalyst, Fischer Tropsch has two sites, the water gas shift active site and the Fischer Tropsch site. If we add all together, it's just one amount of sites, whatever it is. And actually that depends on the oxidation level of the iron. It can go from the reduced iron into the oxidized iron. If it's an oxidized like magnetite, it will be very active in terms of water gas shift. However, water gas shift will change the water into hydrogen, producing a hydrogenation type of environment. We'll reduce that iron that has been oxidized, go back to the Fe2C5, I guess that's the number. That will be the reduced iron, which is again active in Fischer Tropsch. So this equilibrium is made through the whole run. However, if the conversion is pushed too high, the water partial pressure will increase that much and produce sintering. We'll close the catalyst pore and we are going to be losing surface area. And that will show definitely deactivation. Poisoning, we have found several compounds that produce poisoning into the system. However, sulfur is the greatest one. And if we're working with coal, sulfur is always a problem. And fouling depends on how big the molecules that we are producing. Sometimes they get stuck, we call it stuck inside the pores. And sometimes that becomes too heavy, and therefore the chain grows too much, and that cannot be replaced, so therefore there is a diffusion limitation inside the pores. That is linked to the age of the catalyst. Sometimes we call it aging, but it's not by sintering or poisoning, so we have to blame something else, so we call it fouling. The production of oxygenates and olefins is also characterized by iron catalysts, and unfortunately this will increase, at least the oxygenate has to increase the capital cost. If we are looking at caustic wash after the production, if we have too much acid, caustic wash is a need. If we are looking at olefins, either we are going to hydrotreat it or we're going to hydrogenate it. What are we going to do with those olefins? A big market has been opened in terms of alpha olefins. Iron is characterized by the production of olefins, and you can produce almost 60% olefins. So why don't try to sell it? Most of them are alpha olefins, which are very good for detergent markets, so can be sold. Water gas shift is always present, and particle attrition is always a characteristic and sometimes a headache. In terms of cobalt requires low temperature operation, and therefore I explained you already the effect on steam pressure. One has to be careful how low we have to operate. Many researchers have claimed that cobalt is much more active than iron. However, if you look at selectivity of iron is far better than cobalt. And cobalt has been tried to match iron by reducing the temperature and decreasing the methane from it. However, we have to think what it's going to do with the steam that is going to be produced by the reactor. It has a low deactivation and can be regenerated by, Shell said 5 years. We have to wait and see. It's much more expensive catalyst. It costs 30 times more than iron. It's also, if we have a sulfur breakthrough, we basically dump the catalyst, bring something from the stock, from the hopper, which is already there, and come back online. However, we put the numbers in terms of cobalt just to make sure that we're looking at the ballpark. The catalyst will cost more than the capital cost of the reactor itself. The capital is so expensive that has to be paid in 5 years, otherwise it really is not worth it. So we have to have a very efficient, clean gas system that will ensure a very clean gas. And Shell has put a lot of money into the ICI technology with a zinc oxide. It produces a low oxygenates an olefin, so therefore if somebody wants to market alpha olefins, it cannot be done with cobalt. And does not have water gas shift activity, and is a stronger catalyst than iron. This point I should mention because many people have seen to go into cobalt because of the attrition problem. And I don't think that will be enough justification to go to cobalt. Cobalt, since it's a supported catalyst, is much more expensive. And whatever support we use has to be stronger than iron, and therefore it won't break. If I compare Sasol, SSBP, and the Shell middle distillate process in terms of product distribution, basically what I'm comparing is iron and cobalt. What I know the base of iron and what I know the base of cobalt representation here. In terms of fuel gas, cobalt produces 20%, which is very high, double than what I can achieve with iron. The gasoline production is almost the same. However, the diesel production is far higher in the slurry system at Sasol. If I look in detail into the gasoline and the diesel cut, these two are the same catalyst. This is one a fixed bed, and this is a slurry bed. And this is a high temperature at 350 degrees C. Okay, if we focus only on the effect of reactor, one can see that the olefins in the diesel cut is almost double. I was mentioning one of the person here that this is just the effect of the reactor. This is not the effect of the catalyst. These two are similar catalysts, iron catalysts. And this is just the diesel. The diesel cut has almost double the olefins, and most of these are alpha olefins, which are basically can be directed for marketing purposes for detergent. And gasoline also will show a little bit higher in terms of olefins, at least 50% more olefins. And you can see there is no aromatics. And I mentioned to another person here that sometimes the wax that we produce at Sasol, we have to use it for cheese coating, so it has to be food grade. So the requirements for these kind of products, food grade, are very strong in terms of oxygenate acids, organic acids, and also aromatics. I'm now going to shift my talk on the wax-solid separation, since I understand that many people has do some research here. At Sasol, we try to separate the wax from the solid in different processes. This is just one way how we can do it, and we're able to do it, and Professor Davis has a copy of the patent on that. So since he has a copy of the patent ready, there's no problem that I can talk about it. And if we look at the particle sizes and try to identify how difficult, who is the responsible for this difficulty to separate wax from solid. If we are talking of micron sizes, this is 1 micron, there will be 10 microns, and there will be compressible cakes. We're looking now at filtration process. And the whole thing is going to be about filtration. This is incompressible cakes. Basically, it never plugs. The filter will never plug. We have particle sizes from this range. We're looking at this range. Basically, you're looking into trouble. You're already having a cake that is going to be compressed, and whatever you do is not going to clean it. So the problem that we also found is that if you're looking at everything below 5 microns, it's really bad for your separation process. So what we did, that's already in the patent, is that we selected a non-plugging filter. And this is a candle type. We look at candle type that was discharged into a common header. I have like a screen. So the big particles are going to be flashing to this screen, and small particles are just going to go through. So if I want to clean this, I will try to backflash, and anything that is in there will pass back again. However, this won't plug. And this is the type of filter that we use. I think with that you can have a pretty good vision how it looks like. It's just a candle type. This is the screen. So the catalyst will, the wax will go through these slots, and the big particle will be trapped here. And once I want to backflash, I just push the wax there, and whatever was there, use clean, go through that slot. This is the Sassel catalyst. And one thing that I should mention is that the spray drive plays a very important role in this catalyst attrition problem. We found is that, as you can see, these are spherical particles, and these are the same thing, same composition, same thing. However, changes happen in the production plant, which you have dimples. And I guess the people from United Catalysts Incorporated can know this by experience. Once you have dimples and cracks, you're basically talking about a catalyst going to break. There's nothing you can do about it because you started from the beginning with something that already had a problem. And that has to do a lot with moisture and what the binder you're going to use on that. And this is just, although this is the same thing, in terms of chemical composition and everything exactly the same, it's just how you prepare your catalyst is going to define that. We have to put special emphasis on the catalyst preparation. The catalyst preparation was actually many hours that the Slurry team had to be concentrated in. This is the new reactor that we use for the strengthening of the particles. Initially, what we wanted is to put the catalyst, as it comes from the spray dry, directly into the synthesis reactor, where Fischer Tropsch was happening. So the idea was remove some catalyst and put some new catalyst in, hoping that it's going to reduce online and be active. However, due to the partial pressure of water, it never reduces to the full extent. So we were unsuccessful. So we put the catalyst in a single reduction plant, which is this reactor, which is another slurry reactor. It's full with wax, catalysts come in there, and we bubble hydrogen. So the whole reduction is done with hydrogen, and we use existing equipment. So it cost us about $2 million. just the whole operation for commercial sources. So the current operation at this moment is that we receive the catalyst from the catalyst production plant, reduce it before it gets into the Fischer Tropsch process, and thereafter put it in there. Also, I should mention something to somebody here, that as the catalyst ages, attrition comes into the figure, and attrition rate starts increasing, so therefore has to be removed. That catalyst has to be removed from the slurry system. So you actually remove some catalyst, although it's active. You're not removing due to inactivity, you're removing because of attrition. So you remove that and put new catalyst in it. Still active, the old one, but you put new catalyst with a different particle size. So what you're going to end is with an equilibrium particle size that will ensure that your wax-solid separation will work efficiently. And to finish my talk, I just want to mention a few points. That we have reached the stage that we have to optimize the slurry bed in terms of Sasol operation. As I mentioned to you, the slurry bed at Sasol 1 had to fit something that is already there. The marketing was there, the plant was there, the gasifier was there, the H2CO ratio was there, the sulfur removal was there. Everything was there, so we have to fit exactly like a glove in already existing hand. However, if we have to design this from scratch, we'll do it differently. There was a project with a quota gasification that we tried to put a slurry bed between the gasifiers and the methanator reactors, those reactors that produce just methane. And we wanted to put a slurry bed there. That was a new thing. We can do anything there, and we were able to produce something very interesting, compare the iron and the cobalt, and assess what's the effect of the H2CO ratio, and whether they have some sort of steam header, what kind of heat removal system we're going to use, and that kind of consideration has to be done in order to optimize the slurry bed operation. The other thing is that we should mention that we should design slurry bed processes about 10,000 barrels a day in a reactor. This is the size that we should be looking at. Smaller than that will increase your capital cost. I try to use the Bechtel design, the DOE study for the Fischer Tropsch using cobalt. However, it doesn't fit the new catalyst. We need a new design, a new basis to study cobalt. Cobalt needs a high H2CO ratio. If you're looking at commercial alternative for cobalt, you need a high H2CO ratio, which will suit the use of natural gas. Natural gas is a cleaner fuel, it's cheaper to reformate than gasified coal, so therefore we should be looking at cobalt catalyst with natural gas. And it's definitely needed the sulfur removal technology. There's a lot of development that is needed in that. To put zinc oxide is very expensive to put into a commercial plant. You're paying by the pressure drop across that bed, which is a fixed bed, and you're paying by the material. And those are very expensive. However, that can be justified by the cobalt catalyst, which is a very expensive catalyst, so you got to take care of that. In terms of iron, we don't have that problem. However, we would like to have a better system to remove sulfur than only coal methanol. With that, I would like to finish my talk and open the floor for discussion.
Are there any questions?
When you say high hydrogen-CO ratio, what do you mean as far as a lower limit?
For the cobalt,
Yeah.
the cobalt catalyst, one of the characteristics of the cobalt catalyst was that it produces mostly paraffins. And let's say in the scenario that we'll reduce the methane formation to a very low level. So we're looking at a stoichiometric ratio of 2. Okay, a stoichiometric ratio of 2 it will be what the cobalt catalyst has to produce. and because it's mostly paraffins, doesn't produce oxygenate, doesn't produce aromatics, so basically linear paraffins. So the minimum H2CO ratio that I'll put in a very long reactor has to be at least 2. The higher the better. However, that will be the minimum if I can recommend it. This can be achieved by recycling or by shift reaction before.
You mentioned that the amount of olefins in, let's say, diesel is more in a slurry bed rather than a fixed bed.
Yes.
Shouldn't it be the other way around, because the slurry bed has a much greater reaction volume, so there is more chance of hydrogenation?
Okay. This is actual results, so I won't argue with the data, but I'll explain you the theory that is behind it. And it's only a theory, has been discussed within Sassoon group and outside, but it's still very difficult to confirm. The iron is a hydrogenating catalyst. Okay, so if you're looking at a pellet, which is a dimension of 2 millimeters, this side, let's say, and you're looking at a particle of the slurry bed, which is, let's say, 100 microns. So the chances of this molecule to, after reaction and producing an olefin, let's say, finish as an olefin, to travel back 2 millimeters and does not be hydrogenated, and to travel this size and not be hydrogenated. So it's very likely that the olefins will stay as an olefin in a very small particle that travel the whole way in a pellet and don't reach any hydrogenation site. So that's only in terms of particle size. That will explain it. That will try to explain it. I won't say that that's the true explanation, but where we have need to think on that.
So does that mean in the absence of poor diffusion, reabsorption is really a minor thing?
Yes, both of them should be the same. However, it's just a travel through a longer time. It's a residence time within the pore. If you have a very small particle, the residence time will be very small, and therefore will stay as an olefin. The longer the residence time stay in the pore, the most likely that it will become a paraffin.
In your Campbell filter, the filtrate has, is the small particles removed from the filtrate and not recycled?
Okay, let me answer that as well. I discussed this with several people. There are two approaches, and one is to produce a clean liquid, and the other one is to keep the catalyst in the reactor. There are two different things. One focus on the solid, how to keep it in. The other one focus on the liquid, how to have it clean. What we want is, with this, is to keep the solids in. At this moment, who cares about how much solid goes with a liquid? Okay. Why is like that? Because these particles will only represent ppms in terms of part of solids in the liquid. Later, you can separate it with any filter press. Since we are looking at only ppms of concentration, you can do it with several options. You can do these with filter 8, Campbell filters, with anything, because their concentration are very low. Your main concentration is within your slurry, the first filtration, which is 30% or 20% solids. That's very high. So you have to be concerned about the compressibility of the cake. After that, you reduce from 30% or 20% into ppm levels. But basically, you have a clean liquid. Perhaps you cannot see through, but the next step in filtration will ensure that you have a clear flux.
I take it you have to take the small particles out, or else the compressibility problem is going to stay with you.
No, the compressibility here. Oh, you can get away from that if you put, let's say, filter 8.
On the candle filter?
No, outside. That's a different system.
Oh,
Okay. Basically, what you're putting is don't handle the problem in the reactor, handle the problem elsewhere.
right. In your reactor, if you don't remove the small particle, the compressibility problem is going to stay with you.
agree. With that, you're removing selectively.
Right.
All your more particles, and moreover, the filter itself does not allow plugging. But with this, always helps to remove all these fines, especially when there is no cake. The initial filtration, if I plot, let's say, solid concentration with time of filtration, solid concentration will go very high at the beginning. The moment that you have a cake, basically your solid concentration drops very much.
I have a non-technical question.
Yeah.
How has the changing political scene in South Africa affected Fischer Tropsch process, economic viability of Fischer Tropsch process?
Okay, that's an interesting question. Sasol's approach on this has seen before as the political takeover of Mandela. We saw that beforehand, and we said, well, initially Sasol was built for supply of synfuels because of the oil embargo, because of the apartheid and all the things related to that. The oil embargo was imposed on South Africa and actually forced Sasol to produce fuels to keep the industry going. And instead of being that a bad situation, a bad scenario for the country, actually benefited the country because forced all industry to produce whatever they needed, whether it was more expensive or not. It was the only supply. Nobody was importing nothing from outside, either having a closed economy. So South Africa produced up to 60% of the fuels that are needed, Sasol. However, now that everyone can import oil, then the need has changed. So Sasol decided to switch from fuels to chemicals. So nowadays we are already in the polymer business, acrylonitrile fibers, producing methanol, producing MTBE. We have diversified so much, and capital has been poured into different processes to get away from the fuels and to produce more chemicals.
So chemical business isn't subsidized at all by the
Oh, not at all.
industry?
Not at all.
So
At this
it's
moment-
in that case, it's economical for the chemical industry then.
Oh,
Still.
if we're looking at, remember that one thing, the capital cost has already been paid. That's a major chunk in
Okay, yeah.
Fischer Tropsch process. Since we have that, let's say, that period where we were protected from outside world, I'll say protected from the outside world, we paid already the bill. Okay, so now that we don't have any bill to pay the capital cost, it's just a running cost that has to be, and that can be done very easily. Now, also answering your question is that Sasol has gone into the fuel, because it's a major part of Sasol business is fuels. So we produce gasoline. So now we are going into the marketing of the product, competing with everyone else, with Exxon, with Shell, whoever goes into the picture. It's a competitive market nowadays.
What's the sulfur forms? Your last conclusion, you want to remove the sulfur. Is that the hydrogen sulfide?
Okay, what we found is that many research has been done in terms of H2S. However, H2S is not the only compound that poisons your cattle, especially cobalt. Anything that has sulfur will deposit on cobalt. Anything, whatever it is, COS, that will deposit on cobalt. And if we look at a fixed bed, and that's an experience that we have in terms of iron, the gas comes from the top and start reacting from the top down. What we found is that the catalyst from here to there acts like a sulfur trap. Everything was sulfur here. FES. Everything was sulfur, which is basically was protecting the whole tube. You'd rather put 1 foot of reactor length than damage the whole tube, the whole catalyst. So basically we remove the sulfur here. Although it's a very expensive pay to put a sulfur trap there, but we found that sulfur was there. And then reaction takes place here. And the last part, interesting, was that since the water partial pressure, as the reaction goes along, builds, these catalyst that we found at the bottom of the tube, well, has a very low BET area. There's almost no area because of all the sintering problems that it faces with such amount of water that was in the tube.
Is there a measure of hardness of the spray dried or calcined catalyst, or is that possible to say, or how do you measure it? Or
Let me talk in. The only thing is that I can mention, that's a problem, is that how to express the tendency to break up. That's basically the question. How to express, because what we found is that, and that's a latest paper of Dr. Espinosa, was that if, let's say you have a particle and it's very strong, and you have a particle that is not that strong, and both of them breaks, which is better? The problem that we find out that the stronger how it breaks is the worst, because it's like, and that was, you were going to laugh on that. I was explained by one of the engineers and called the cracker theory. You have a cracker and you crush it into two pieces. You break it into two pieces. The two pieces of the cracker or the cookie that you have are never going to have the problem. It's the little pieces that just crumble down. Those little pieces, those are the ones that are going to give a headache, because those are the sub-micron particles, below 5 microns. Those are the ones that are going to be responsible for the separation process, for plugging your filters, for plugging everything. Not the big two chunks. So what we decided is rather have something that is not that strong, but that can agglomerate a lot, that will have a very strong binding. So if you have like a crack, you have basically like a very moist biscuit. You chop it in two and nothing comes out. That's what we actually wanted. If that breaks, let it break, but doesn't disintegrate. So we did it like that, and this is one thing is that we improve with this technique, this process. And one other thing that I should mention also is that there is one thing to work with oxidized catalyst, and the other one is to work with reduced catalyst. Magnetite is not the same as hematite. It's not the same thing. So one thing is that we were very careful is that once we extract the wax, let's say we want to measure something in one catalyst from the reactor. Once we extract the wax and remove everything from it, we have to keep it either in a hydrogenation environment with hydrogen, or we have to have it in a nitrogen environment. The moment that we expose to air, it's already oxidized. And it actually, if it's oxidized, it would not resemble what's happening in the reactor, because basically magnetite will only produce water ship, it will not produce Fischer Tropsch unless it reduces it. So that's one of the limitations of looking at attrition problems outside the reactor. But answering your question is, one thing is that we measured was how much particle, how many particles, the ppm that passed through these. So if we put ppm and time, we're going to have like that. So we integrate these and we will know how much particles are in the system, so we characterize those catalysts against those. But it's very difficult to characterize outside. You can build this in lab scale. You can buy this and basically express it like that. Yes?
Is the hardness benefit inherent in the cobalt, or could that development process be used to re-improve the iron-based catalyst?
The cobalt is a supported material. Basically it has alumina, silica, titanium, zirconia, whatever it's going to be, is very strong by itself, without any metal, active metal. It's very strong. So, basically it produces very nicely spheres. And then after can be impregnated with something else. However, the iron does not have support, that's why it's very cheap. It's just a co-precipitator, and this is just after it's co-precipitated and re-slurry, then you basically you have that spray dry. And so it's a matter of cost, I believe. Iron has been always look at the characteristic that is cheap, is readily available, and can be disposed very easily. The moment that we change those characteristics, we have to rethink of the utilization of iron. It will become too expensive just to dump it. And the economy could change a lot.